Let's have a look at a couple of examples from section 5.5, starting with exercise 4. The instructions here are to find the first four terms of the following recursively defined sequence. So we've got a recurrence relation, d sub k equals k times the square of d sub k minus 1 for all integers k greater than or equal to 1. And then d naught, or d sub 0, is equal to 3. That's our initial condition. So when we write out the first four terms, we're going to start with that initial condition. And then we just follow that rule that the recurrence relation gives us. So d sub 1 would be 1 times 3 squared. D sub 2, now that we know what d sub 1 is, d sub 2 is 2 times 9 squared. And so on, and we can stop there at d sub 3, which is 78,732. So that gives us a little practice working with a recurrence relation to generate terms. Now let's look at another example, which is exercise 22. Now what this example gets into is it takes the Fibonacci sequence, which is discussed in this section, and it looks at the way in which it can be used to model rabbit populations, and that's discussed in the book. The idea is we've got a couple of rules for what happens from month to month, and that's going to help us determine the recurrence relation. So in this exercise, it takes that and modifies it a little bit to see how that would change things from the traditional Fibonacci sequence. So here are the rules that we'll follow for this model for rabbit population. Rabbit pairs are not fertile during their first month of life, but thereafter give birth to 4 new male-female pairs at the end of each month. So that that amount of offspring is where the change is from the original. And no rabbits die was also in the original rule set for the population model. Part A of this exercise says let R sub n equal the number of rabbit pairs alive at the end of each month n for each number n greater than or equal to 1, and let R sub 0 equal 1. So that R sub 0 equaling 1 just means that at the very beginning of the year, which we can think of as the end of the 0th month, which doesn't really make sense, but fits in, where at the end of the first month, the end of January would be R sub 1, end of February would be R sub 2. So the beginning of the year would be that R sub 0. And they're giving us our initial condition. So R sub 1 is also going to be 1. Now, we don't have a recurrence relation yet. We're going to work toward that. R sub 1 has to be 1, though, based on those rules, because rabbit pairs are not fertile during their first month of life. So that original rabbit pair will still be alive at the end of the first month, but will not have produced any offspring. Now, at the end of the second month, that original pair is still there, but now they've produced 4 pairs of offspring. Okay, so that means at the end of February, at the end of the second month, there'll be 5 pairs of rabbits. At the end of the next month, okay, at the end of March, we'll have those 5 that were around at the end of February, plus 4 offspring from the 1 pair that's fertile at that point. Remember, 4 of those pairs were just born the previous month, so they're not fertile yet. And then we can keep going in this fashion, and by continuing this process, we kind of begin to see what the pattern is, how we use the previous values to get the next value. And so the recurrence relation, based on what we're seeing here, is r sub k equals r sub k minus 1 plus 4 times r sub k minus 2 for k greater than or equal to 2. And let me just briefly put this in the context of the rabbits, and you can compare this to the original Fibonacci sequence, which would not have the recurrence relation, which would not have the coefficient 4 there. So the r sub k minus 1 is the number of pairs that were around at the end of the previous month. And we know that none of the rabbits are dying, so they'll always carry on to the next month. And then 4 times the number of pairs that were alive 2 months prior, because that r sub k minus 2 represents the number of mature rabbit pairs. And so we have a number of offspring equal to 4 times that. Okay, now this is not the end of the problem. Part B of this is going to ask us to continue this process and compute r sub 5 and r sub 6. And actually, if you look at this problem in the textbook, the instructions are a little bit different, but it's asking us to go up through r sub 6. We already did up through r sub 4, so this is all that's left to do to get those values up through the end of the 6th month. So at the end of the 5th month, we've got 65 pairs. At the end of the 6th month, we have 181 pairs. How many rabbits will there be at the end of the year? Now, we don't have an explicit formula, so we can't just say, well, let me plug in 12. But we don't have that far to go to get r sub 12. And if you use something like Excel or maybe a little program, you can generate this pretty quickly. And even just doing this by hand is not going to be that great amount of work. So we get r sub 12 is 49,661 pairs of rabbits. Okay, so we're seeing this population grow quite rapidly. And that's the end of this problem. So I hope you found this helpful. You do have a problem on your homework that's kind of along the same lines of making a slight change to the original, Fibonacci rabbit population model. And I'll see you in the next video.